So in a previous lesson, I commented on the idea that any complex number can be written in the form a plus bi. So it doesn't matter what you do with a complex number, you can always express it in that way. In today's lesson, I want to talk about a different representation of complex numbers, and that representation is using an Argand diagram, which is effectively a graph. And it's a really very simple thing. Suppose that you had 3 minus 2i, and you wanted to express that as an Argand diagram. What you do is basically just draw a two-dimensional, like Cartesian graph, but instead of making the horizontal axis the x-axis and the vertical axis the y-axis, we're going to call this the real axis, and this will be the imaginary axis. And so when we graph 3 minus 2i, we just think about going to 3 on the real axis, negative 2 on the imaginary axis, and some teachers will say that the complex number is, that point. I really think it makes sense for us to think about this as effectively a vector that's going to that point. And one of the things that's neat about thinking about that as a vector is it allows us to think, if you remember from what we learned about polar, it lets us think about this complex number as not just an a plus bi form, but effectively as being a magnitude and some sort of angle. Right? Rather than think about this as being that point, we can think about it as this being some angle theta, and this being, some length that this complex number has. And so, one of the other things that I need to do in this, other than show you how to draw these diagrams, which I hope you can see is very simple, is how do we find the argument of a complex number? How do we find the modulus of a complex number? So first of all, notation, right? The angle, we're going to be calling the argument. Right? So if I ask us to find the argument of this complex number, I would write that as arg of 3 minus 2i. And the way that we do that, the easiest way to do it is using inverse tangent. And again, I hope you remember that from the stuff we did with polar. You're looking at the inverse tangent of the y component over the x component. Right? And if we take that and plug it into the calculator, I'm going to pause and go do that. Alright, so I got this angle to be negative 0.588. Sorry, that doesn't fit over there very well. Negative 0.588. And so we keep in mind when you do arctangent, you're always working with you're fighting with principal values. So when you get this thing, you may have to add pi to it. In our case, this angle seems to be down, so it seems like that's going to work fine for us. And so that's our argument. We've got negative 0.588. So finding the magnitude, or sometimes called the modulus, is in some sense easier, because really what you're doing is you're just thinking about the Pythagorean theorem. That angle, we're basically looking at having 3 here and 2 here. So if you wanted the modulus of 3 minus 2i, we're really just looking at doing the square root of 3 squared plus negative 2 squared, which gets us the square root of 13. Right? So we had our argument up here, we have our modulus down here. Fairly simple things. For the argument, you're just doing the inverse tangent of the y component over the x component, and for the modulus, you're basically just doing a Pythagorean theorem. I've got a couple examples of this that I want us to take a look at, so we'll do those, and we're going to lead into something really awesome after that. So let's see where we end up. So the example I have here is I want us to find the argument of w and the argument of z, given these complex numbers that we have here, and then I want us to find the modulus as well. And I want us to do all this stuff in radian mode just because I think it's good practice. So I would say pause the video, draw these things as I didn't write it down, but draw those as Argand diagrams as well. Draw the Argand diagrams and then find the argument and moduli. Alright, so for w, you've got 3 and 4. So you've sort of got the idea that w complex numbers right there. Finding the argument of w just means that we need to do the inverse tangent of the y component over the x component, so that's 4 over 3. Again, I'll pause and hop over to the calculator app to check that. So I found this to be 0.927 radians. And again, that answer seems reasonable because, the thing that I have here is in the first quadrant. That seems like a reasonable thing for me to find for the argument. While I'm here, I'm going to go ahead and do the modulus of W as well. The modulus of W should be the square root of 3 squared plus 4 squared, which is 5. Right? So we found the argument, we found the modulus. We'll do the same thing for Z. Right? First, on the Argand diagram, you're looking at roughly negative 5, 12, and so we're looking at roughly there. The argument of this thing, the argument of Z, is going to be the inverse tangent of the y component over the x component, so that's 12 over negative 5. When we throw that at our calculator, alright, so I got negative 1.176, and I hope that red flags, I'll even underline it in red, or maybe cross it out in red. I hope red flags are going off, because that's definitely not a negative angle, right? What that found you was the principal value of the arctangent of 12 over negative 5. We want pi plus that. So if I take the answer that we previously had and add pi to it, we'll come up with sort of the modified answer, the correct answer, which I'll bring up now. I got 1.966 for that argument. The modulus of this one, again, not a big deal. If you want to know what the modulus of Z is, we just do the square root of 5 squared plus 12 squared. I suppose it's negative 5 squared, but it's not going to make a difference. Long story short, this is another Pythagorean triple, so this is going to end up being 13. Okay, so hopefully not a big deal. I want to do one last thing in this lesson, and that's I want to look at what happens when we multiply complex numbers, and so I'm going to do that in this next slide. So using Z and W that we just did, I want us to first find WZ, then find the argument of WZ and the modulus of WZ, and then take a look at those numbers and the numbers we just found on the previous page and see if you see some sort of a connection there. So again, I'd say pause the video, try that on your own. So for part A, when we find WZ, it means we're going to need to do 3 plus 4i times negative 5 plus 12i, which means we'll sort of go through the full FOIL process for this. This is going to be negative 15 plus 36i minus 20i plus 48i squared. Sort of check my work there. 15, 36, negative 20. That seems alright. We've got negative 15 here. This is going to be negative 48. So you'll end up with negative 63 because the I squared is going to turn, I squared will turn this into a minus. These other two things will combine together and give me plus 16i. So great. That thing there is my WZ. Yeah, that seems alright. So then the argument of that thing. If I want the argument of WZ, I'm supposed to do the inverse tangent of 16 over negative 63. And so I'll bring that up over here in just a second. And I got negative 0.249. Now it's worth taking a moment to investigate whether that makes sense. Just think about this complex number. On an Argand diagram, this is supposed to be negative 63, and 16 is supposed to be over here. Which means I'm more than likely, not even more than likely, I need to take this answer and add pi to it so that I'm getting the appropriate value. So I'll do that next. So I ended up with 2.893 as the argument for this thing. Okay. Next, I want to look at the magnitude. Right, so if I want to look at the magnitude or the modulus of WZ, I'm going to need to do the square root of 63 squared plus 16 squared, and I'm going to skip the arithmetic on this one. Turns out that's 65. Right. Now part C is really the exciting part of this problem, and the part that I want you to think about. And unfortunately, in the video, the way I'm recording it, I can't go back and look at my answers from before. But if you've kept track of them on your paper, what I want you to notice is, and it's probably most clear on the modulus, the modulus of the product was 65, and the two individual moduli that we got before were 5 and 13. And I don't know if you recognize it, but 5 times 13 is 65. And so it sort of leads us to the idea that if you want to know the argument of WZ, it's equal to the argument of one of them times, I'm sorry, That's completely wrong. I was jumping ahead of myself. We're looking at the modulus, right? The modulus of WZ is equal to the modulus of W times the modulus of Z. And this is a property. This is a thing that we can sort of memorize and use from this point forward. We'll box it in 2 different colors so that it stands out. So that's a relationship for the modulus. For argument, and again, I can't go back and show it to you, but look at the 2 arguments that you had before. I think you'll find that if you add the 2 arguments you had before together, you'll get this 2.893. And so the property that we'll have there is this idea that if you want the argument of W times Z, it's going to be the argument of W plus the argument of Z. And we're totally going to use that to our advantage later. I mean, when we get into later lessons, there's not going to be a whole lot with it, with the homework and the problems today. But these are relationships that I wanted you guys to see. So that's the end of this one. We've got more stuff coming in the next videos.